All right, Form 6, analyzing energy for simple harmonic oscillators from graphs. Yay! We're just going to look at graphs. I don't think there's really any math on these that you have to calculate, but kind of remembering what you've been doing for some past units will be really helpful. So since it's talking about energy, I hope that kind of maybe triggers this one over here, kinetic energy. And then we have a spring, so maybe that kind of triggers this one down here. And that's kind of it. So maybe it's kind of a misnomer here, this simple harmonic motion part. But once we keep doing more of these and more practice, hopefully it will get a little easier. There definitely are some tricks to these questions though. So looking at the first one, and again, let's just keep in mind that kinetic energy is 1/2 mv squared, and potential energy for a spring, that's what that little s is just 1/2 kx squared. So we have some 2 kilogram block attached to an ideal spring, and it goes horizontally. So our spring kind of mass system, we have one of these kind of setups right here. And there's no friction. That's kind of nice. And we're given velocity versus time. So that's kind of interesting. We're not given x, we're given v and t, which best represents the spring potential energy over time. So essentially, we're being asked to figure out what would the graph of this be. And since we're given velocity and we're given the mass, we're actually kind of given this. And now we know that mechanical energy, like the total energy, is the sum of the kinetic and the potential. So let's think about this. In the beginning, if there's zero velocity, well, there's zero kinetic energy. So that one's zero, actually. So that means if we're not losing any energy because there's no friction, it says there's no friction. If there's no kinetic energy, it must be all spring energy right here. So we're going to have the maximum spring energy at 0 seconds. So we're looking for a graph that has maximum energy at 0 seconds. And mine kind of cut off right here. So sorry about that. Maybe, yeah, it looks like I can't really just drag that up either, which is kind of awkward. Actually, maybe I can do this. If I come over here and I do that, and then maybe I can paste that in and just bring it up a little bit. Oh, that's awkward. Maybe it won't let me. So I don't know. I'm sure we'll figure this out. We'll struggle through. Oh no, there it will let me. So something like that. That's just kind of a little more helpful for it. We can kind of see it better that way. So essentially, we're saying that we're looking for some graph that is the maximum of the spring energy. That's what we're actually asking to find here, being asked to find. So this one has zero energy at 0 seconds. This has negative energy at 0 seconds. Well, what the heck is negative energy? I don't even know what negative energy is. Things can lose energy, but the energy isn't negative. So we know that this option C and it looks like option D are kind of off the table already. So maybe that kind of helps us a little bit. So we can kind of get rid of these two and go, well, this one doesn't make any sense, and this one doesn't really make any sense because we don't really have negative energy. And actually, that kind of tells us that B doesn't make any sense either, because even when it's all kinetic energy, we're still not going to have negative potential energy. So automatically, we know this one has to be A. So that's kind of weird. We just kind of did that one by deduction, knowing that energy is not something that can be negative. But let's look at this just a little more, just to make sure we kind of get it. If we're at our maximum velocity of 3 centimeters per second at 1 second, well, if we're at our maximum velocity, we're all kinetic energy then. It's all kinetic right here. So if it's all kinetic, there's zero potential. Well, it turns out that this graph has zero potential at 1 second, and our maximum right there at 0 seconds. And then again, if it has, again, zero velocity at 2 seconds, well, it's going to have the maximum potential energy. If it has no velocity, there's no kinetic energy. That's zero. So that means it's all spring potential. So again, this graph does in fact match. So that kind of clears this one up. Now, if you're a mathy person and you wanted to do the math on it, you could have actually plugged into this 1/2 mv squared and said, well, 1/2 0.2 kilograms, and then you would have had to take the maximum velocity of 3 centimeters per second, turn into 0.03 meters per second, and then we square that, and we do 0.5 times our 0.2 times 0.03 squared, and I end up getting a really tiny number. It's actually not even popping up for me on my calculator, but it actually does turn out to be this kind of 0.00009 right there. So we could have done this with math or just kind of looking at the graphs. So let's look at our next one here. So we have some mass block. It's on a spring. It goes horizontally still. There's no friction. That's nice. We're given a velocity graph again, and we're saying which graph represents the kinetic energy of it over time. So our last question was asking about our potential energy over time. This one's asking about the kinetic energy over time. And we're actually given the same exact initial kind of graph as in the previous question, our first question. So again, kind of looking at this, I see that, well, if there's zero velocity here, it has to have zero kinetic energy. So K is 0 here. And then if we're at our max velocity, well, we have that our kinetic energy is whatever this max value is. And then here, our velocity is negative, but since kinetic energy is 1/2 mv squared, even if v is negative 3 centimeters per second, and I square that, I'm still going to get a positive 9 centimeters squared over second squared. So here, this is still actually K of a max value, and I skipped one, sorry. If our velocity is at 0, again, we have no kinetic energy. It's the same here, and it's the same at this last point at 0, and then the rest of these just match. We have our max values at kind of our crests and troughs, and so really we're looking for something that actually kind of matches this. So which graph has 0 at 0 seconds? Well, this one's out of the picture. This one has 0 at 0 seconds, and at 1 second, it is at a max, and then at 2 seconds, it's at 0, so this kind of matches, and then at 3 seconds, it's at a max, and then at 4 seconds, it's at 0, and then at 5 seconds, it's actually at a max, and then at 6 seconds, it's at 0. So it must be this one. So I'm just going to assume that. We can always erase it, but let's actually look at these last couple here. So neither of these, this one starts actually way up here at a positive value, so that one's already just off the table, and this one starts at a negative. So we are correct. It is, in fact, B for that one. So moving on, this time we're given a spring constant. We know K. We're given the initial displacement at 0 seconds is 0 centimeters. So essentially it's starting nowhere. So okay, that's really useful. We're starting nowhere. Cool. And then we're given a position versus time graph. And we're being asked to find which of the following answer choices represents the potential energy over time. So again, this is Roy saying, can you find the graph that shows this? And really, this is kind of the mathy way to represent it, but which thing shows the potential energy? And so if in the beginning, we know the spring constant, we know K, we know the initial displacement is 0, so it starts at 0. That's really all we're being told. And this kind of looks like the same graph, but instead of having velocity here, we actually have position. So it's asking us to find potential energy over time. Sorry about that. And so looking at this, well, in the beginning, our displacement or position, this kind of is x. So wherever x is 0 in this equation, our potential energy is going to just be 0 in this equation. So we're at 0 here. We're at 0 at 2 seconds. We're at 0 at 4 seconds. We're at 0 at 6 seconds. And I can maybe just go through already and kind of get rid of some of these answer choices just by knowing that much, that wherever the heck x is 0, the potential energy is 0 for it. So I'm looking for zeros at 0, 2, 4, and 6. So this one, do I have zeros at 0 seconds and 2 and 4 and 6? No, it's the opposite. This one's garbage. Do I have zeros at 0 and 2 and 4 and 6. No, option B is also utter garbage. What about option C? We have zeros at 0 and 2 and 4 and 6. Oh, we do. And this one, we have zeros at 0 and 2 and 4 and 6. Now, this one's shifted. So just kind of by deduction, again, we can maybe guess that it's C. But let's do a little more thinking on this. Well, when it's the farthest away, and since it's x squared, it doesn't matter if this x is negative or positive because we're going to square it. So if we're squaring, I don't know, -3, we're going to get +9 still. So that means that at 1 second and at 3 seconds and at 5 seconds, our spring potential energy is a max. That's true when we're right here. Whoa. Right there and right there. And that one actually should be for the potential energy. And that's also true way down here. So we are looking for something that has a max at 1 and 3 and 5 seconds. Well, do we have a max at 1 second? We do. And at 3, yeah. And at 5, yeah, we totally do. So this one, in fact, is option C. Now, I would challenge you to think about this and go, well, what about the velocity? What would the velocity one look like? Well, since there's no friction here, and this total energy is conserved because there's no friction, our kinetic and our potential must be kind of combine to make this total energy. At 0 and 2 and 4 and 6, there's 0 potential energy. That's 0. So that means all the energy is kinetic. And then at the opposite moments, when our potential energy is a max at 1 and 3 and 5 seconds, it's all potential. So this one then is a 0, and then our potential is actually a max. And so what that really tells me is that when one's a max, the other's 0. When the other's a max, the original is 0. And so these graphs are kind of opposites of each other. So the neat thing is that this option D right here actually is the kinetic energy graph. Because if we're thinking about it, we're going to zoom in a little bit. At 0 seconds, since there's no potential energy, it's going through equilibrium. That kind of makes sense. If we kind of drew a picture here, and I have my box, my block, and this is, let's say, equilibrium, and I had earlier pulled it back over here, and I let go, and it's zooming this way. The spring force is pulling it towards equilibrium, actually. Well, right here, the spring isn't doing anything. It's moving the fastest when it's at equilibrium. So that would be right here at 0, kind of on our scale, because this graph is kind of symmetrically around this x-axis, actually. And so that tells me then that, hey, right there, 0 seconds, I'm going to start at whatever this maximum value is. And then down at 1 second, well, at 1 second, we said that it's all spring potential energy. It's the maximum x value, so it's all this potential energy here. So then we must have 0 kinetic. And these two kind of switch back and forth and back and forth and back. And so these two always kind of swap out. And what that ends up giving us then is energy is conserved. So if I were to like go and draw a line for the total energy of it, it's always the same value. It's just this total E value. And I think one of the videos you took notes on actually showed this, because even if I took kind of the red and the blue right at this spot and I added them together, they would give me this purple value across the top. So energy is conserved, and that's kind of how that one works. So I think we have, what, 2 more? No, last one. Okay. So we have some block. It's attached to an ideal spring. It oscillates horizontally. There's no friction. We're given a spring constant, and we're given x. Well, that's kind of cool. That already tells me, before even reading anymore, 1/2 kx squared, I could just calculate that. I could calculate what my initial displacement is and what kind of my initial potential energy would be. I could just do the math on it. I'd have 1/2. Well, then we have 100 newtons per meter. Oh, that looks kind of sloppy. Let's do newtons per meter. Maybe it's just as sloppy. And then we don't want to have this in centimeters still, but 3 centimeters, that's the same as 0.03 meters, because we took the decimal, moved it 2 spots over. So 0.03 meters, and we got to square that. Do not forget the square. That's the most common mistake people make, is they just forget squares for whatever reason. In the gravity law and Coulomb's electrostatic kind of force law, everyone always forgets that little squared for whatever reason. And so that tells me that, oh, our initial potential energy, well, that's 0.045. Well, it's energy. Energy's in joules. So we kind of know some mathy number, I guess. And we're given some position time graph. And it's asking which graph represents the kinetic energy. So this is actually kind of like the second question we did. We keep getting asked either what's the kinetic or what's the potential look like. Well, if we think about it, and we're starting at our maximum kind of displacement, because it's going to go, just looking at the graph, it either goes 3 positive or it goes 3 negative here. Well, that just tells me x is positive 3 or negative 3 centimeters. So I have maximum potential energy right here, and right here, and here, and here. So these are like potential energy is when it's at its max value right there, and right there, and all the way over there, and way over there. Okay, so we're looking for something that has like with potential is at a max here. That means that at these points, the kinetic energy is a minimum, right? Because if the energy is conserved and it's all potential, that means none of it's kinetic. So we're kind of looking at this through the potential energy side, but you could think about it and go, well, if the potential is a max, that means the kinetic must be a minimum, which is kind of bizarre to think about. So maybe we just add that, and K is a minimum. So really, we're looking for a kinetic energy graph that has, essentially, if it's all potential here, that means there's no kinetics. So we're looking for a graph that has zeros, because there's minimal or no kinetic energy at 0 seconds, and at 2 seconds, and at 4, and at 6. So 0, 2, 4, 6. Which graph has zeros at 0, 2, 4, and 6? Well, this one does. What about the next one? None of the others actually have zeros at 2 and 4 and 6. None of them. So I'm assuming it actually must be option A, but let's just think a little more just to be sure, like if this was a test or something. Well, if we have zeros there and we look at it right here, kind of these new points where this graph has zeros, well, if the x value, this is really our x value, if our x value is 0, well, that means that there's no spring potential energy, right? If x is 0, the u, our potential energy, is 0. So if there's no potential here, it must be all kinetic then. So these points at 1 second and 3 and 5 must all be kinetic energy. So we want something that has max values at 1 and 3 and 5. Well, does option A have maxes at 1 second? Yeah. What about 3? Yeah. What about 5? Absolutely. So it totally is this option A right there. So hope the graphs kind of made sense. Let me know if you have any questions.